we're going to talk about automatic differentiation. And before we talk about automatic differentiation, maybe we should talk about manual differentiation a little bit. So I don't want to go very deep into this, but I do want to provide one motivating example. So if you'll bear with me. Okay. The main problem we want to solve is, if you can imagine the following situation. I have this graph right here, and I happen to know that this graph has an equation, the y-coordinate on the graph is equal to x squared. I bring this up because this is like the easiest non-trivial example. So this goes through a couple of points, and one of the points, it's not to scale maybe, but let's say one of the points it goes through is 3, 9. So the x-coordinate is 3, the y-coordinate, use the formula, would be 9. Right. So the basic problem is we're going to draw a red line right here. And that red line, we want it to be tangent to this curve. And what I mean by tangent, I'm not going to say. Just, we can kind of look at that and we can say, okay, that's tangent to the curve, okay. And we want to find the slope of this red line. Normally, when you want to find the slope of a line, you have this handy formula you can use. The formula that you like to use is you take the change in the y values, and you take the change in the x values, and you divide those. And this gives you a measure of how steep this line is. Okay, so this is great. We can use this formula. Now, what do we need to use this formula? Well, we need a point. Here's a point. We need another point. And if we don't know another point on this red line a priori, then at this point, we're kind of out of luck. So that's unfortunate. But remember how we kind of said, okay, well, this line is kind of special. This line is tangent, whatever that means, to this curve. And so what that means is, well, if we zoom in really close, see these points on this curve are very close to the red line. At least if we're close to this point, right? Okay. So what we're going to do is we're going to give up trying to find the slope of the red line. It's impossible. Can't do it because we need 2 points on the line. So what we're going to do instead is we have this equation. This equation lets us get new points, but not on the line, on the curve. Okay, so we'll pick a point really close to 3. Like a number really close to 3 is like maybe 2. Okay, I could probably think of some closer points, but let's say that. And we're going to make this green line. And this green line, we think, okay, that green line is kind of close to the red line. And the green line, it's easy to calculate the slope of. The slope of the green line is 9 minus 4 over 3 minus 2. So 5. So that's really easy to calculate the slope of the green line. But it's not really that, it's not really close to the slope of the red line, as close as we'd like. So there's an obvious thing we can do to get a line that is closer in slope to the red line. What is the obvious thing? Right, scoot this point closer. Exactly.
Question.
Yes.
Where is this data coming from?
Huh?
Where is how is this function defined? Is it defined tabularly? Is it a sampling of some continuous thing? Is it a noisy signal from the real world? Is it a closed form expression?
You said, where is this data coming from?
The thing we're trying to differentiate.
And I am wondering what you mean by this data.
It's a closed form.
Motivating expression.
It's a closed form expression defining some smooth function.
Yeah.
I don't know if I know all the words in that sentence to be able to parse it together. I apologize. But I mean, the thing...
Is this weather data, temperature or humidity, or is this an algebraic expression that's infinitely differentiable or smooth?
There's no data.
It's the nice function
Differentiating
on the
some
right-hand corner of the graph.
Yeah.
Okay.
Yeah. So when I do functional programming, what I do is back to the checking for the null pointer. What I do is I assume that the caller is satisfying their contract. Okay? So I'm not going to worry about where this comes from. Does it make sense? I'm just going to say, assume that we have this picture, and I would like to know the slope of the red line. And if we make that assumption, then I can take you on a ride. And if we can't make that assumption, then we're going to have to stay put.
I want to go on a ride.
Me too.
Okay. All right. So we have this picture, and we have this equation that tells us the points on here, and we want to know the slope of the red line. Okay. So I get what you're asking, and it is totally incidental to this example. So for this example, just say we could get as close as we want. Okay? So we say
we can evaluate that function anywhere on its infinite variable.
anywhere.
Okay.
Yep. Right. And with real data, you can't do this.
That's right.
Right. But fortunately, this is a made-up example.
That doesn't mean anything.
Yeah. Yes. Okay. So, we can pick a point that's closer, and we can get a line that is closer in slope to the red line. So this might motivate a question. Well, why are we satisfied with just picking closer points? Why don't we pick the same damn point and plug that in and figure out the slope then? Can we do that?
No.
Oh. That wouldn't work, right. Okay, so we're going to have to simply pick closer and closer and closer points. Okay. Now, we can implement this. But I think it's pretty straightforward to implement. I'm not gonna, I was thinking about implementing that, but no, let's not do that. We'll move on later. So what we can do, so the process is, we're going to make an estimate by picking a nearby point. And then we understand that our estimate is not perfect, so we actually form a sequence of estimates, and we keep taking closer and closer estimates until we're somehow satisfied with the result. How we're doing that, that's completely subjective, okay? But at least if we want to do it on paper, we can in principle do that. We can in principle just say, okay, I'm going to take closer and closer points, and when I'm satisfied, I'm going to say that I'm done, and I'm going to say this is not exactly the slope, but it's close enough. Okay. Well, if we implement that in the computer, that does break down. So if we implement the algorithm exactly as I described it in the computer, what's the problem there? Well, you can tell it I want you to run for 1,000 years and then give me the answer, whatever it may be.
Floating point precision.
Floating point precision. Oh, right. This is a problem. Right. If we're doing this on paper, we can in principle calculate these points however close we want. But if we're doing this on a computer, then we can't.
It cuts off some.
Right, it cuts off at a certain point. So there are two problems. One problem is it could take a long time to run, or the complexity is very complicated. So the nice thing about this, if you think of this as a computation that you want to do, is very simple. But then if you think about that algorithm I described, for such a simple expression right here, the algorithm I described is very expensive. Estimating over and over again. So it's very expensive. The other thing is, once you get an answer, can you trust your answer?
When the floats get close, it should get pretty wiggly.
Yeah, when the floats get close, it should get, I don't know that I know what that means either. But I'll take your word for it that we can't really trust the answer if we implement the thing that I described. And so the real thing is, if we want to implement it for this function, it's probably great, it's probably fine, because this function is very smooth. which is kind of a way to kind of numerically measure how quickly a function changes. This function is a perfectly fine function, but a lot of the functions that people deal with are not smooth. They're still differentiable, but they're not smooth, and they are and round-off error is a very big problem. So the process I just described is numerical differentiation. You estimate, you make a better estimate, you make a better estimate, and then somehow you decide that you're happy and you're done and you stop. And it has the drawbacks of being computationally expensive, and you worry about round-off error. Okay. So people have been doing problems like this on paper for a long time. And they've been doing it for a very long time, but they didn't make progress until people started to make abstractions. So the abstraction I want to talk about is, we picked a specific point here, and we plugged it into this formula, and we got a number. Okay? This seems okay. Well, mathematics deals with numbers. Okay? So we take a point, or we take a number, plug it into the function, it becomes a point, and we work with these numbers. The abstraction that we want to do is we want to say, okay, wait a second. Let's not actually work with numbers. Let's take the slope formula. I don't know why I erased it. But let's actually say, you know what? Let's not pick our numbers ahead of time. So instead of picking our numbers ahead of time, I'm going to say this is, say, x1. And let's actually say, what would this formula give us if we plug like a number? Let's do it a little bit easier. Let's say that this is a number b. And so this number would be b squared. And let's say this is a number that we haven't decided yet. Let's call it a squared. And let's do the slope formula, not on numbers, but on these kind of abstract numbers. So we're going to do the slope formula. B squared minus a squared over b minus a. And once we do that, we can start using algebra on this. Okay, so if we had 2 points, this would be the slope between them. If we had 2 points. Well, we can further simplify this. So we say, okay, if we had 2 points, this would be the slope between them. Okay? All right. And remember what we said earlier? How can we get it to be exact? We want those points to be the same. Well, on this level, we can pretend that those points are the same. And we arrive at 2b. And now let's say at this point, what did we want b to be? We wanted b to be 3. And so what's the slope? 6. Okay. So what helped us there? What helped us there was abstraction. Go ahead.
Wait, so if b is b and b, isn't the denominator 0?
That's yes. Yep. So what breaks down is this step. So what we have to do is we have to say why this step is not actually a problem. Okay? But for hundreds of years, like no joke, people said, yeah, I know this really doesn't make sense, but it gives the right answer, so it must be right. So this is actually, for hundreds of years, that was the response. They said, Jesus, this is too good to ignore. Then there were some people, like the Berkeley, the bishop, who UC Berkeley is named after. He brought up exactly what you just brought up. So, you're in good company there. This is a problem, and it has to be worked out. But for hundreds of years, people ignored it because this technique is just too powerful. So what is it we said earlier? Earlier we said, okay, you know what? We are shit out of luck. We can't find the answer. We're just going to have to estimate it. And what did we just do?
Not estimate it.
We found the answer, and it's exact. So we went to a problem that was intractable to all of a sudden, well, now we could do it. And you know what? This is easier than crunching all those numbers. Does that make sense? So yeah, you're right. There's something weird going on, but we're just going to sweep it under the rug, and that's if we keep doing these talks for 100 years, maybe we'll get to it.
It's undefined behavior. It's okay.
Okay. So the thing that helps us here is abstraction. What did we do? Well, we're working with every point on this is a pair of numbers. So we're thinking of this as this is a bunch of pairs of numbers. Well, what if we don't think of it that way? What if we think of it as a promise to carry out some computation in the future? Okay? So I really like this because this illustrates two of my favorite abstractions in Haskell are functors and lazy evaluation. And this is neither of those, but it kind of like this kind of inspires those. The idea that the first thing we're going to do is we're going to plug in 3, and then we're going to calculate slope, and we're going to get an answer. Well, what if we reverse that a little bit? What if we calculate the slope first, and then plug in 3? So once we do that, we're treating our points not really as just numbers, but as kind of data in and of themselves. And we're thinking of the graph as not a way to generate data, but we're thinking of the graph and the equation itself as data that we can manipulate and act on. And that's really the abstraction that helps us here, is our procedure has become data that we can act on and use abstractly. So we're doing the same stuff, but on a different level. And so that's kind of the idea behind a functor as well. You kind of do the same stuff, but on a different level. As I said, this is neither of those, but it kind of like, to me, it kind of is a similar idea. Okay. So this is how people do derivatives with paper. Actually, I lie. It's not. This is not how people do derivatives on paper, because we can take it one abstraction further. So one abstraction further is what we ended up getting here is we got a formula into which we can choose the number b. And we get a formula for the slope. Well, what is that b? That b is an x value. So what if we don't plug in the 6, and we now focus our attention on this guy, and we say, okay, slope is 2b for any b value. Now, the b in here, where did the b come from? The b is an artifact of the notation I used here. But what is the b really in the larger context of the problem? If we forget this, the b is an x value. So let's inline that. So the slope at any point is 2x. So think about how many computations we would have to do to get the slope at one point. I mean, a computer could do it really fast, right? But if we want to do that, we'd have to do a lot more computations than just finding the point itself. And now what if we wanted to find the slope at millions of points? And we had to estimate each of those. You know what? This is very difficult. Let's do it once in abstract. Remember that formula. And now when we want to do millions of computations, we have a formula that we want to do millions of slopes. We have a formula whose complexity is not any greater than the original. So that's pretty cool. Okay. All right, so numerical differentiation. Anybody who does scientific computing knows about numerical differentiation, which is where you estimate, your computer estimates progressively better and better estimates, right? But it suffers from those problems. The complexity is high, and and you can't trust the answers, okay? Well, on paper, we can find the formula for the slope. The formula for the slope, the complexity is small, and it gives exact answers. But how did we find it? I mean, we just did some mechanical stuff. We just did some manipulations. In principle, a computer should be able to do all of that as well. That's automatic differentiation. In automatic differentiation, the computer produces a formula, not a formula, an algorithm for the derivative. The complexity of that algorithm is bounded in terms of the complexity of the original algorithm, and it produces results up to machine accuracy. So let's do it. Okay. Before we do it, we have to see how people do derivatives. And we're going to teach the computer to do exactly the same thing. Okay. So a couple derivative rules. Let's say if f is a function, and when I say function, I don't really mean like a Haskell function, but I mean like a mathematical function where you plug in a number and you get a number. Okay? And let's say df is the derivative of f. So df has a type, r to r, if it exists. The derivative, what is a derivative? It's that formula for the slope that we found. When our function was x squared, the derivative was 2x. Okay? So if f is a function, and if df is a derivative of f, so in particular df will also be a function, then there are a couple of rules that people use to make taking derivatives easy. So this first one is if we have a constant times our function, I'm going to pull that out. Sorry, if f and g are functions, we have a sum of functions. We take the derivative of each piece separately. If we have a product of functions, there is this strange thing we can do to find the derivative of a product of two functions. Wow. Anybody who's taking calculus recognizes that as the product rule, but if you don't recognize it, just take my word for it. If you want the derivative of a product of two functions, let's say f times g, then this is how you can find it very easily. All of these are worked out by hand, and then basically worked out by hand once, and then used to take the derivatives of more complicated functions. We're going to teach the computer how to do that. Okay. There's a little trick, and I'm going to give away the trick right now. The trick is that we...
Can everyone see it fine?
Yeah, can everybody see it fine? That's a great question.
Nope. Slightly small.
Is it slightly small? Okay. Okay. So we're going to make a data type that we're going to pass around. It's going to be a dual A. Dual just means that because there are two, so it just means two A's. Why is it not a pair? No reason. There's really no deeper reason. It could just be a pair. And I'm lazy, so we're going to derive some instances for it. And what we're going to do is we're going to teach the computer the derivative rules that I wrote down right here. How are we going to do that? Okay. Well, what we do with these functions is we add them, we multiply them, we do various things. So the functions are kind of like numbers. So I'm going to write a num instance. Let's say if A is a num, then dual A is also a num. And now we have to implement num instances for these. Oh, what does num have? Okay, it has plus, and it has times, and it has minus, and it has, yeah, absolute value, and it has signum, and it has from integer. And all of these have to be duals. So I'm going to pattern match on here. And I'm going to give this a suggestive name. Okay. Okay. So how are we going to add duals? Adding duals is pretty simple. We're going to add the first two. And we're going to add the second two. So this is how we add duals. That's not very interesting. Okay, you're right. It's not very interesting. How are we going to multiply duals? This is where it kind of gets real. We're going to multiply the first coordinates. And then what are we going to do with the second coordinates? We're going to multiply in this funny way. Okay. Where is that funny multiplication coming from? Where have we seen it before? So we saw it earlier today on the board, but we want to take the derivative of a pair of functions. So what this dual data structure is doing is it's keeping track of two things at the same time. It's keeping track of a number. Why a number? Well, if A is a number, it's keeping track of a number, and it's keeping track of another number, and the first number it's keeping track of is going to be added and multiplied in the way that normal numbers are. But the second numbers are going to be added and multiplied according to the derivative rules. Let's keep going. So how would we implement minus? Yep. And fortunately, since all of these are numbers, addition using negate has a shortcut, right? So what we're doing here, what is this minus? Remember, this minus is the num instance for A, whereas this minus, the one we're defining, right? So we're defining it in terms of the operations on A. And why are we defining the minus in a usual subtraction? And we're defining the multiplication in this weird way. We're really just following the derivative rules. Oh, wait a second. Do we have a rule for minusing functions? Shit, I forgot that. Okay, well, what's the rule for minusing functions? Well, thanks to rule 1, if you think of this as being plus and negative 1, exactly as we were saying there. Okay. So absolute value. This is a little bit difficult, so I have to all the rest. Let me just copy those because they're not that interesting. These ones are ones that you have to work out by hand, and then once you find the answer, you encode it. So let's put those in there. So what is that? That's what is this? This is don't worry about that. This is worked out, like I said, this is worked out in advance. So if you know the derivative rules and you can take derivatives, you can work this out in advance. Let's see, and then from integer. This one's a little bit interesting. So from integer is supposed to take an A and give us a dual. And so what we're using here is from integer for A. That's going to be the first guy. And then the second guy is going to be 0. Why is it going to be 0? Yeah. So what is my dual keeping track of? If we think of this if we think of the motivating example, the dual is keeping track of two things. The first thing that the dual is keeping track of is the point on the graph, the y value of the point on the graph. And the second number is keeping track of the slope of the graph at that point. And that's why it's following the derivative rules when we want to write this instance. Well, what if we don't have a point on the graph? What if we just have a plain ordinary integer? Well, then we can kind of ignore it. It's not doing anything. It doesn't have a slope. Okay. So, what can we do with this? So we're going to load a GHCI. And going to, let's let up a function. And let's make sure that it only works on nums. So we're going to limit ourselves to these 6 methods. So let's say something like x plus 3 times x.
You might have to make that bigger too.
Oh no. Can we see that? Okay. Let's do that. X plus 3 times x times x. All right. Why am I not just writing x squared?
What's the type of that double star?
Oh, shit. That would make it floating, right? Okay, so we're just going to do this. Okay. So type of f. All right, yeah. So it's, okay, this is great. Okay. So let's take f and let's apply it to dual 3, 0. I got dual 30, 0. Okay, what's the 30 doing? What if I did f of just 30? No, what I mean is f of 3. We just did f of 3. That's 30, right? Okay. So f of dual 3, 0. So the 30 is the function value, and then the 0. What is that? That's weird. Well, what if I do dual of f applied to dual 3, 1? And we get dual 30, 19. This is all very fascinating. Let's actually go back to the function that we were doing earlier. I think that will be more interesting. So the function we were looking at earlier was x squared, y equals x squared. So let's look at that. So that's our g. And let's do this. Let's do g applied to 3. It's obviously 9. Let's do g applied to dual 3, 1. 9 and 6. What is the 6? That's the slope that we wanted. Okay. All right, so that's neat. This is neat. But it's a little bit weird. Why do we have to put this 1 in here? What if we put 2 in there instead? This is so freaking weird. Why do we have to put a 1 right there? This will actually end up being not a weakness. It'll be an asset. That we have to put this 1 in there. Okay? So let's go on forward. I also want to be able to take derivatives of fractionals. So I'm going to put that in there. Let's see. Fractional A implies fractional dual A. So we need a way for dividing duals. And how do we divide the first of the pair? It's just regular division, whatever the division for A is. How do we divide the second? Well, if you're taking calculus, you just remember the quotient rule. Or you don't, but you at one time saw the quotient rule.
Look it up in the book.
Yeah, I had to look at, no, some of these I had to look up in a book. Yeah. So you can look up the quotient rule in a book. You can encode it right here. This is really just the quotient rule. And now we have a fractional instance. So we can save that. Okay. And we can have division in our functions now. Let's say x plus 1 over x. And the type of f is fractional. And we can just apply f to a dual number. And so the claim here is that the value of the function at x equals 3 is 3 point whatever, and that the slope at that point is 0.8888.
Is it?
Yeah, it is. We can verify it, but it is. Except for the 5. So we don't suffer from round-off error when we're doing this, but we still suffer from machine precision. Well, let me see. We suffer from round-off error, but it's not as bad as with numerical. That's what I mean. Yeah. We still suffer from some round-off error, but these answers are correct up to machine precision. So that's pretty cool. These ones are.
So it doesn't accumulate error?
Yeah, estimates don't accumulate error, right. So there's still error in doing this formula, but that's all the error. And so you could put a bound on it. Yeah. Yeah, thank you. Okay, now enterprising scientific computing people need to work with floatings usually. So here is, yeah, if you've ever defined a floating instance, there's a lot you have to define. So let's see, what we have here is we have to say who pi is if we want a floating instance. Pi in the dual land is dual pi 0. And why is the second one 0 here? Because pi is a constant, and derivative of constant is 0. Okay. Yeah. All right. So how about the derivative of the exponential function? Well, let's see. The first one is, so exponent of u. That's the easy part. This one probably warrants a little explaining. What is it? It's u prime times exponent of u. Where does that u prime come from? Well, if you're taking calculus, I don't want to go too far into it, but you have the chain rule from calculus. Okay? So we are encoding the chain rule in each and every rule that we do. If you look at every single rule, if you say, okay, what's the derivative of logarithm of x? It's just 1 over x. Why didn't I put 1 over x? I put u prime over x for the possibility that we have a chain rule that we have to take care of. So inside every problem, we implement the chain rule. And if you don't know what that means, that's okay. But just trust me, if we wanted to implement the chain rule, you can imagine it being very, very difficult. Well, we are encoding it in every single other rule. So we don't have to implement the chain rule. That's a benefit there. Okay. So we have the derivative of square root, the derivative of sine, cosine, tangent, arc sine, arc cosine, arc tangent, hyperbolic sine. And again, the second part here, you really you look it up in a book. What's the derivative of hyperbolic sine? Well, hyperbolic cosine. How do I know that? Because I looked it up in a book one time. Okay. We are teaching the computer how people take derivatives. And so we're teaching them all the derivative rules. Difficult rule here is exponentiation. We write out 3 cases. In theory, the third case is most general. You have u prime raised to a v prime. And my other 2 are more less general. So the third one should be more general. But we actually need these because the third one runs into a problem if, say, v prime is 0. Here's v prime. And v prime is 0. There's this part where we have to, I guess it doesn't run into a problem. But it really runs into a problem if u prime is 0. I don't know. Actually, I can't really see why. But we have 3 different cases for that. The division. We divide by u, but that should be fine. Oh, is that the one problem that, well, let me take the logarithm. Anyway, what ends up being the most boring rule in calculus? The derivative of x raised to the n power is n times x to the n minus 1. So this is like, I say boring. It's really like your workhorse in a calculus course. This is what pays the bills. Ends up being kind of difficult to implement here, just because here we have n times u raised to the n minus 1, and I'm forgetting something. I'm forgetting u prime there, and a v prime here. But anyway, I just thought that was a little bit interesting. This is, the first derivative rule that you learn ends up being kind of a little bit hard to implement.
So if you delete the first 2, will it still work?
Now let's do that.
Just comment that
Yeah. Okay.
things happen and you don't comment.
Okay, so let's make something that is definitely a floating. Let's say, and definitely uses exponents. So let's say let f of x equal, say, x squared minus 3. Let's just keep it simple, x squared. That's the same example we looked at earlier. So f of x is x squared. So of course when we apply this to 3, we get 9. Yeah. When we apply this to 3, 1, remember 1 is our magic second input if we want to get the right answer. We get 9, 6. That works fine. Actually, where does it break? Where's the division?
Try it with x to the x.
X to the x?
That,
Let g x equal x to the x. The type of g is, yeah, okay, that's great. So let's say, so it works fine. But what if, that works fine. Then we get dual 1, not a number. So then it doesn't look like it works fine. The thing is, I don't think uncommenting these is going to fix your problem. Let's try that. Okay, so we need this g. And we want to apply that to dual 3, 1. And we want to apply it to dual 0, 1. Still broken. So that's unfortunate. Okay. But what about our f? So let's comment these out again. And let's get our f back. F is just plain old ordinary x squared, no problem. And let's find the f applied to dual 0, 1. So just spoiler, the answer is supposed to be 0. And we get not a number. Okay, that's unfortunate. Now how about if we say let h of x equal x times x. And let's apply g to dual 0, 1. And we get the answer that we're supposed to get, 0, 0. Let's make this a little bigger. That's bizarre, right? So the problem is right here. So dividing by u. And who is u? U is the first guy in our first dual. And we're doing this function applied to this dual. Oh. Yep, that'll do it. Okay, so that's why we need cases for this. Okay. So this is all well and good, but it's a little bit weird that we have to pass around this 1 all the time.
Question back.
Yeah.
The division is by 0. Your case doesn't trap out the u 0. It traps out the u prime being 0.
Yep. No, wait, no, the division here is by u. And this case right here has the u equals 0.
Right, and your earlier cases check on u prime being 0.
Oh, this one?
No, in the code
No,
that's
yeah.
off the screen,
Your pattern matching.
your pattern matching. That first line checks for u prime 0.
Yeah, it does. Oh, yes, but it has a simpler expression that doesn't involve division. That's why. So you're right. Yeah, it doesn't. This expression and this expression are equivalent as long as u is not 0. But if u is 0, remember that dividing that we did? This is the same problem, or a similar problem.
Why does that bottom one, why does u equal 0 end up in those first 2 lines instead of in the third one?
Because yeah, let's look at that. So let's step through execution. So let's reload this and let's let up the problem child. It's x star star squared, right? Okay? And let's apply g to dual 0, 1. And the answer we're supposed to get is 0, 0. Get not a number. Yeah, we're supposed to get 0, 0. Did we load the right one? Did we not have this working like a minute ago? Oh, there it is. I must not have saved or something like that. Okay, so we have this version of the code, and we have this result. And the question is, why does this call result in the first code path being followed and not the third code path? Is that right? Yeah, why is that? Why is it that this function call results in the first code path being followed?
2 is the constant.
2 is a constant, and we have a from. I don't think we have a from double, but where do we? Somewhere, something is casting this 2 as a dual 2, 0. I don't know if it's from rational or not. From rational? From rational is casting our 2 as a dual 2, 0. And that's why we're following the first code path rather than the second, or rather than the third. Even though it doesn't look like, it looks like, well, this doesn't guard against, it's our u prime that should be 0. And our u prime actually, or our v prime rather, and it actually is, because it's just this 2 right here. So anyway, if that's really subtle, it was really subtle for me too. The first time I did this, I was like, oh my God, why is it broken? It couldn't do this problem, right? And it took me a little while to figure it out. Does it kind of make sense? Oh, okay, good, yeah.
So if you raise it to itself, it'll break though?
Yeah, yep.
Would another case fix that? Or should it?
I think I think it is supposed to fail simply because I have extra knowledge, right?
So
but
it's a part of the contract.
Not the way that the program is written this way. So, if you want to do this for numerical computation, there are still a lot of special cases that you'd have to write out. Okay? So there is an abundance of special cases, and we're not going to worry about them right now. But yes, that's one of them. Yeah.
So can you give us some examples of real world problems in which automatic differentiation provides us with an answer that we couldn't get any other way?
Absolutely, I have one prepared. But it kind of depends on your idea of real world, because it is an algorithm that you couldn't write down, so it's a code block, and you could not write a mathematical formula for it, but we can still get the derivative. Well, and to me, that qualifies as real world, but I don't, we'll see. Whether or not it does, it may be splitting hairs. I don't know. Okay, so what are we missing here? What we're missing, I'm going to write a couple more instances. One more instance, actually. I'm going to write an ORed instance. And this ORed instance is really just for bookkeeping. Basically just how do you turn a pair into an ORed? You just look at the first component. That has nothing to do with derivatives, but this is to satisfy some type checking that has to happen later. Okay? And now, that pesky number 1, it's a little bit weird to be passing that number 1 in. Normally in calculus, you think, okay, I have a function, and I want to find its derivative. And you don't normally plug in numbers one at a time, like we're doing here. We plug in a number 1 at a time. That's not really what you want to do. So we'll just make a wrapper for this construct that we've been doing, and we'll call it little d. And little d takes a dual to dual and gives you an A to A, or A to C, a dual A to a dual C. And this is a little bit weird to kind of look at that, but let's look at an example. So let's look at the type of G. G is a floating A to A. Let's actually make sure that we have loaded this code. Oh, diff dual. Oh yeah, I wrote a bunch of accessors that I didn't write. Yeah, here, okay. Here's some getters and setters. Okay.
Could we
look at those? Yeah. Okay. So const dual requires a number, takes an A and gives you a dual A, and I think of it as casting the number as a constant in duals. So your number and 0. Seed dual takes 2 A's and just packages them. Eval dual reads the first number, or the first datum, and diff dual reads the second. The idea behind the names here is, remember what this dual is keeping track of. The first datum here is the value of the function. The second one here is the value of its derivative. So that's behind the names. But really, it's just, if you wrote a pair and you wanted getters and setters, this is probably how you would write them. Okay. So this function is just going to put that idea of passing a dual 1 to the function behind a wrapper, because it's a little bit artificial. So let's get our function. And let's look at the type. The type of G is floating A to A. And let's look at the type of DG. It is floating C, eq C, so it picks up a little bit of baggage, but C to C. So it's DG is not acting on duals. DG is just acting on numbers. So what we did dual, let's take our G, we apply it to dual 3, 1, and we get dual 9, 6. That's the function value and the derivative at 3. Well, let's apply DG simply to the number 3. And we don't need that artificial 1 right there. And we get 6. So what is DG in our code? DG is the derivative of the function G. So so we can't look at it. There's no show. The people who wrote Haskell forgot to write a show instance for functions. But anyway, this is an actual Haskell function. That's kind of the point here. So this is where automatic differentiation is not symbolic differentiation. If you ever use like Wolfram Alpha, you can ask it to find the derivative of a function. That's symbolic differentiation. And what we're doing here is fundamentally different. We're not, our G is not really a symbolic function. We could write a formula for it, but what is it? It's a Haskell function. And our DG, its derivative, is not really, it's not a symbolic kind of mathematical function. Well, it is a mathematical function, but it's not a symbolic like algebra function. It is a Haskell, function. It's a computer subroutine, right? So this is interesting. We have a representation for the subroutine in memory, and hey, we have a representation for its derivative in memory, and we can call it, and its complexity is bounded in terms of the complexity of G.
How did the EQ constraint show up?
Because we are putting the number 1 in. So in order to cast that 1, it has to be some equatable type. Yeah, we have polymorphic number literals.
I think it's because you have 0 case in your for the case matching.
Oh, we have eq here. Yeah, never mind.
It gets like each sugar into a eq case.
Yeah, why is it?
Because you're working over like some polymorphic A type, right? So it's
Yeah.
not like if it was an integer or something, it would just, it knows exactly how to do the integer.
Yeah.
Just on those, but because it's polymorphic, it has to use the class.
Okay. Yeah.
We're doing the pattern after 0.
Yeah. Yeah.
So I'm pretty happy with Phil's answer to Alex's question because I really didn't have a very satisfying answer. I just,
I just spotted the eco when you basically
Yeah, I'm sneaking stuff in there, like this ORD class. Why is that there? That has nothing to do with math, as far as I know. Okay, so I have some examples prepped. Let's see. Our first example is, this is a function. Okay, we already saw a couple functions. I mean, we can take their derivative. So we get the derivative of this function. What is this function? It's x squared minus 3x. If we could get an expression for its derivative, it would be 2 times x minus 3. Now Haskell's not going to give us an expression for df because it's represented as an abstract syntax tree in the computer. Okay, well, maybe, I don't know. I don't really understand it. But this is what, if we were going to take the derivative by hand, we would get. And if we plug 4 into that, we'd go 4 times 2 is 8, minus 3, we'd get 5. So this is giving us the correct result in that case. And it actually is not too hard to see if you kind of go through the code. It gives us the correct answer. We look at all these cases. I wouldn't want to think about checking all these. Well, I mean, I wrote them, so I trust them. But anyway. So that's the first example. Now, that number 1 that we have to pass around, it's kind of like a little bit of baggage. But it actually becomes an asset because what we get here is this system that we've done in about, what was it, like 60 lines of code, is going to work for multivariable functions as well. It is not limited to just single variable functions. It's going to work for multivariable functions for free. So algebraically, say we have a function x squared minus 3xy plus 2y squared. This function has what's called a partial derivative with respect to x. And if you've done a lot of calculus, you know what that means. But if you haven't, don't worry about it. Just multivariable functions gets more complicated. You have a partial derivative with respect to x. You have a partial derivative with respect to y. And you have something called a gradient, which is really just taking those two partial derivatives and packaging them together. Okay? So a lot of times when people see, oh, I wrote this computer software to take derivatives, the first thing that real life numerical analyst asks is they ask, well, can it do multivariable functions? And then you go, well, no, I'm sorry, and then you go back home. This one is going to do that. So let's look at the type. I wrote F in the comments, but it's G in the code. That's a anti-pattern. Okay, it takes 2 A's and gives you an A. Okay, and let's look at the type of DG. What is it? Error. Couldn't match. We can't use D. But what we can do is we can take our G and we can apply it manually to a couple duals. So we can go dual to 1, dual, say 1, 0. It's picking arbitrary stuff. What is happening? Get rid of the dollar? Okay. Oh, yeah. Okay. Thank you. Okay. So what do we get? We get dual 0, 1. Again, this has the same meaning from before. The first number there is the value of the function. If you're going to plug 2 for x and 1 for y into this expression, you're going to get 0. You can check that now, or you can believe me. If you were going to plug the same x value, 2 for x, 1 for y, into the partial with respect to x, you would get 1. Let's check that real quick. So we plug 2 for x, 1 for y, so we get 4 minus 3, we get 1. Well, so what we've done is we've taken, by passing it a dual where the first argument has a 1 for its second datum, and the second argument has a 0. What we've done is we've taken the derivative of that function with respect to the first argument, and we've pretended that the second argument is constant. So this is the partial derivative with respect to x. We could do the partial derivative with respect to y. And usually people want to take a gradient, or they want to take the partial derivative with respect to a vector. So if I have a vector like 3 and -2, you think of that as being a direction. And you say, okay, I want to take the derivative of this function in the direction 3, -2. And we get it for free. So what code did we do in order to get multivariable derivatives? It's the same thing we did for regular derivatives. We got it for free. That's kind of neat. Okay, now this is the big one, and this is why automatic differentiation is important, okay? Works for non-symbolic algorithms. I got this example from a gentleman's WordPress. I'll put all the references at the end. But what we have here is, this is a freaking, let's ignore that for a little bit and let's like write it on the board because I can't read that. Let's see, this is for I in 1 to 100. Okay, we're going to do set x equals 0 for I in 1 to 100. Let's see, x equals sine of x plus plus what? Plus z? Yeah. I put the. Let's actually look at that because I forgot how to write imperative code. I'm sorry, it's been so long.
Holding x constant and z is getting out of the
Yeah,
range of number.
yeah. It's throwing away the number, and it is. Let's see. X is a constant. Yeah.
So the z is the listed index.
Okay. So given x, set y to 0. Or set z to 0, let's use the same letters. Set z to 0 for I, no, this is wrong. Shit. Let me just look at it. That's a wrong screen. Yeah. Yeah, it's in the comments. I'm looking for it. There it is. Okay. So this is something that maybe people wouldn't call a function because you can't really write it down. Okay, what is this? This is for, let's see, we function set y equal to x. So we're given x, we set y equal to x, and for the numbers 1 to 100, y equals, we reassign y to sine of x plus y. And then when we're done, we return y. So let's write that down on the board because I'm going to switch to the computer and then show why my thing is the same. Okay. Given x, set y equal to x for I equals 1 to 100. Y equals sine of x plus y. Return y. This was my example of a real life problem. It's real life in the sense that you can't write a formula for it. And I think most functions in real life you can't write a formula for. Okay, so let's go back to the code here. And let's make sure that this does the same thing. So first off, I is not used in the body of the loop. And that's exactly what we have here. I is not used. Here's an accumulator if we want to do a fold. So here is the list element. We throw it away. Here's the accumulator. That's their y. So let's do that. Like so. Yeah, change it somewhere. Okay? And we are applying sine of x plus the accumulator. And then we return that when we're done. So this does the same thing? Okay. How would we write this down, if just mathematically? So the first thing we have to do is we have to take sine of x plus x. And then this is now our accumulator. So what do we do with that? We add x and we take sine again. And then what do we do with this? We add x and we take sine again. And then what do we do with that?
Add x sine again?
Yeah, this is, yeah. And we have to do this a lot, like 100 times. So in principle, you could write this function down, in principle. But in practice, you wouldn't want to. Okay? So does that kind of make sense here? Okay? All right. Let's take the derivative of that. So our function is called h. Let's go into GHC. GHCI, everybody can see it? Okay, let's look at the type of h. H is an algorithm that works on floating numbers. At least I would call it an algorithm if this were a different programming language, but in Haskell it's still just a function, right? Let's do g of h at 3. And we have the derivative. Let's do d of h at 4, at 5, and wherever let's go at 0. Let's go at 0.1. And if we were doing symbolic differentiation, we would have to, well, first off, we'd have to write this down. Write this down. Write it as a closed form formula. So it would involve 100 sign of these. And then our program that does symbolic differentiation then would have to, parse that out into an abstract syntax tree, and do a bunch of derivatives to each piece on the tree, and then give us another expression. So that's great. We could do that, but I think a lot of functions that people work with in real life just can't be written down. They're functions in the sense that you plug something in, you get something out, but you can't really write them down in practice. And so this is just my token example of one of those things. So the thing they say in the automatic differentiation community is they say automatic differentiation is better than symbolic differentiation because automatic differentiation can find the derivative of an algorithm. Well, in Haskell Club, algorithms are functions. So what is the big deal? So what they really mean is automatic differentiation works even if you can't write your function algebraically. That's what they mean. So the function, we can't write it down algebraically. I mean, we can, but there are some that we can't, and no problem. What about this guy? This is fibs. Not exactly. Not exactly. So this is turned into a continuous function. So what are we doing? So okay, fib x is x, or fib x is 0 if x is less than 0. Fib x is x if x is less than or equal to 2 and greater than 0. Otherwise, fib x is fib of x minus 1 plus fib of x minus 2. What this is kind of a continuous version of the Fibonacci function. So it doesn't start out the same, but once you get to a certain level, it gives you the expected result for integers. But this also works on on decimals, on any float. So let's look at that. Okay, so everything loaded. Let's look at the type of fib. So ord A. That's why I have ord in there. Or maybe no, I have ord in here because of this. Anyway, A to A. And let's actually look at, let's see, fib. Let's map it over 0 to 10. So we get, okay, it doesn't start out right. It should be 1, 1, 2, 3, you know. But eventually we start getting the Fibonacci numbers from this. Okay? But we can also, it works anyway, because we have a function that agrees with the Fibonacci on integers, but we can also plug decimals into it. And we can take the derivative. So let's look at derivative of fib at 5. And the number we get is 5.
Does that one also obey the Fibonacci recurrence relation?
That's a good question. Let's look at, we get 6. We get 8. We plug in 7. We get 13. We plug in 8. We get 21. Let's actually plug duals into here. Fib of dual, let's see, 3, 1. We get 3, 2. How about fib of dual 4, 1? 5, 1. 6, 1. 7, 1. What's the derivative of the Fibonacci sequence then? The derivative in these second numbers, 3, 5, 8, 13, 21, that is also the Fibonacci sequence. Let's see, map df over 1 to 10. So 3, 5, 7, that's not right. Oh, d fib, sorry. There we go. 1, 1, 2, 3. Oh, it's the right Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13, 21, and so on and so forth. So why is the derivative of the Fibonacci sequence the Fibonacci sequence? What does the derivative tell us? It tells us how much our function is changing at that instant. So how much are you adding to the Fibonacci sequence when the Fibonacci sequence is 34? To get to the next step, how much do you add? 21. So that's how much the Fibonacci, so this makes sense a little bit. Well, where it doesn't make sense is at 0. Derivative of the Fibonacci sequence is 0 at 0. Let's go fib dual 0, 1. That's dual 0, 0. This is actually a lie, and this is a gaping hole in my implementation here. So we want to actually graph my fib function. It looks something like this. Below 0, it's just 0. From 0 to 2 is x. So it's a sharp turn right here. And then after that, it's basically kind of an exponential function. It's like a curve like that. Okay? This is like a if you tried to like graph an exponential curve on like an Atari. And so what happens is, well, my software here that we wrote is telling me that the derivative at 0 is 0, that the slope of the tangent line here is 0. And the question you have to ask is, well, which tangent line? There's one that looks like that, and there's one that looks like that. Yeah, so this is another one of those special cases. If you're going to use this for actual scientific computation, there's a huge list of special cases. And this is one of them.
Is there a correct answer for this case?
Is there a what?
Which one's the correct answer?
So the correct answer is that the question is malformed. So you say, what's the derivative of the tangent line? Well, your problem is with the word the.
That's true.
Yeah, right, yeah. So the correct, if you want to say that there's a correct answer to your question, it would be that this question is unanswerable. Yeah. No, I mean, that's that happens more often than you'd think. Yeah, I mean, like, well, happens all the time. Will my program terminate? Yeah. Yes, there's a bold statement there, yes. So there are lots of questions that are just unanswerable, and this is one of them. Okay, so let's see, how much time do we have? Okay. Oh, it's been a while. I may have overpromised. Okay, so I said that we would do maybe symbolic differentiation if we got to it. Now this is where this is where I start to show my inexperience. So when we want symbolic differentiation, I basically have to copy all of my same code. So here's what we're going to do for symbolic differentiation. This is exactly coming from someone's blog. Like the other stuff like I worked out, I don't want to say I'm the first person who worked out. There's a library that does this, and I'll tell you the library. But I didn't have to consult anyone else's code to do this. But to do symbolic, I just lifted it from a guy's blog. So this is not my code. Okay, we're going to define some infix operations, plus and times. We are going to make a type for representing algebraic expressions. So data, an expr, algebraic expression of A, is either a variable that holds a char, or a var that holds a char, or a const, which holds an A, or it's plus 2 exprs, or it's times 2 exprs. Now, if we were going to make an actual symbolic differentiation, we would want to write a really nice instance for show here, but I'm a little bit lazy. I'm just going to derive it. So I'll point out, where this would help us later. But right now, I'm just going to derive show. Another thing is this eq. We would really definitely want to write an instance for eq, because right now, 2 expressions that are algebraically the same are not going to be detected as being the same with the derived eq instance. So that's bad. But I just had to put these in here to get the rest of the code below to compile. But yeah, so those are 2 code debts I'm taking out. And we're going to write a num instance. So remember what we did for autodiff. We defined a data struct to hold the location and the derivative at that location. And then we did num, fractional, and floating instances for that. So we're going to follow the same kind of example. We're going to do a num instance for these exprs.
So are you not reusing your autodiff code for?
I am not. Yeah, this is if. So what I'm hoping is that someone will give me a pull request to fix that.
For that derivative,
Yeah.
instead of writing the derivative rules, I think you can just you can use dual numbers, because you have num here, so that implies num dual of exprs.
Okay, let's look at this. Let's load this, and let's see it work, and then let's try that. Okay? All right, so let's just walk through this real quick. I'm duplicating the same code, but I have a num instance for exprs, and I teach the computer how to add exprs, teach the computer how to multiply exprs, I teach the computer how to subtract exprs, and absolute value and signum, I'm going to leave them as undefined just because I don't use them in this example. So this is, this code will blow up, without warning. From integers, it's going to have a constant. And here's kind of why I don't think I'm going to be able to reuse my code. The next thing I do after making a num instance, the num instance is really just to construct these things. And the actual derivative happens here in this function. So deriv takes an expr and gives you an expr. And so we have deriv of var x is const 1. Derivative of x is 1. Derivative of constant is 0. Derivative of the sum of 2 expressions is the sum of their derivatives. Derivative of the product of 2 expressions is the product of their derivatives. And here I wrote a function. Well, I lie. This one is a math function. It is not a Haskell function. It is it's got kind star. So yeah, so that's unfortunate. It's not an actual function. We can't plug numbers into this. But what can we do with it? Well, it looks pretty in the console. So let's get out of here and let's go into GHCI. Symbolic failed. What's going on? Star. On what line?
Oh, it's not recognizing that that's a comment because there's something. Happens.
Yeah. Okay. Just get rid of that. Thank you. Okay. So let's look at the type of fx. This is a function in the mathematical sense, but really it's an expr of integers. And let's derive fx. And what we get is, well, we get an expression that is the derivative, but it's not very simple, and it's not very pretty. So this works in that it gives you an expression that is the derivative if you parse it out. But what we really want to do if we want to make like a computer algebra system is we want to write nice instances for show and eq. So first off, we're looking at this and we're looking at just the way it's declared. And we want to say, okay, well, I want, first of all, constant 1 times something else. I want that to reduce to just the something else. So you want to like implement all of the algebra rules so that you can simplify these expressions. And in order to do that, you have to write an eq instance to know which expressions are equal to which other expressions. And this is not going to do that. If you want to see all of that, and this gentleman implements it fully, like implements all the stuff that I'm not implementing, you can see it right here in this block. But again, it's not automatic differentiation, and it's not using the same code. Do we want to see if we can fix it?
I think you can do it with the num instance, right?
So it's a num, right? So let's do this. Okay, we can just import autodiff, and deriv is its own thing, so there's no name collision. So let's reload. We have autodiff in addition to our other stuff. Let's look at the type of fx. It's an expr integer. And we want to, well...
You want to apply it to the actual function, right? You want to say like the of the function lambda x goes to like x squared, for example, but then apply it to dual var x 1.
Right. What we've been doing before is stuff like this. And this is not going to work. Why? Because, well, is fx a Haskell function? No way. Yeah, you can't. Yeah. Right. So a challenge here for using that code is, well, we want some kind of way to take an expression and turn it into a function. Now, we can take an expression and we can get a number out of it. But like we can pass an expression and a number, and we can teach the computer how to just navigate the AST and get the value out of the expression. But then what do we plug into dual 3.1? I guess maybe we plug that into dual 3.1.
You just make a lambda.
Yeah. Okay. Let's see it. So okay, what do we do? Lambda.
So d first, right?
Okay. D. Lambda.
Like x goes to x squared or something?
X goes to x squared, or let's keep it in num.
Sure.
Yeah. Okay.
But then you need to pass like some num, right? So this is follow up in num, so we're going to choose like what dual of x per or something. So it's going to be dual of, and then you want an x per on the left, so it's going to be var x something. And then you want this to be changing like velocity 1, so you just say like constant 1.
Brice has a chart, so it's part of the class.
Yeah. So, okay, if this works, I'm going to be ecstatic. I'm glad you came. Yeah.
I'm thinking of like, when I look at dual, I'm thinking of like, this is like x plus delta x, or like delta x times the velocity. Like, you want a symbolic expression for like the jet at x that goes off the velocity 1.
Okay, yeah. Let's see. Let's look at what this.
We discovered a valve.
You can pass it.
So we have a dual. Here's the original expression, right? This is. Oh, this is wonderful. So this is how the machine represents our lambda. Is that right? No, it's not right.
Do it.
Yeah.
Do that same thing without the d in front. So that'll give you the function and its derivative. That'll give you a dual thing. The first one will be the thing, and the second.
Yeah. Okay. Wait. So here is how the machine represents our lambda as an expr. And here is the derivative. So what Phil was saying was right. It just had the derivative and the second derivative, I think. Okay, well, okay, so, okay, who wants to make Wolfram alpha obsolete? Oh, that'll take a little work. But now, so the derivative here is 1 times x plus x times 1. So we know that that simplifies to 2x. How are we going to put that into our differentiation? It's going to come down to writing instances for show and eq. So that's I'm very happy. Yeah, that this just works. Yeah.
It'll come down to that if you want GHCI to put it down.
Mm-hmm.
However, I would say that it would probably be better to write your own function to do it so that you're not abusing show or eq.
Break it into 2 steps.
Okay,
Simplify and then show.
Yeah, display instead of show or something like that.
Yes.
Or
Yeah.
simplify.
Yeah. Oh no, you still need a simplify function, but you have to recurse that function and you have to check for equality at each step.
But
you might want to do it even if you're not planning to show it on screen.
Okay.
So it's sort of a separate operation.
Okay, yeah.
only because if you start abusing the Haskell type classes to display things, you break contracts with other codes.
Yeah.
Might not be a big problem because it's show and eq, but we probably shouldn't do it.
Okay. Well, this was the best magic trick I have all day, so I don't have anything that will top that. So thank you all for your attention. And we keep taking closer and closer estimates until we're somehow satisfied with the result. How we're doing that, that's completely subjective, okay? But at least if we want to do it on paper, we can in principle do that. We can in principle just say, okay, I'm going to take closer and closer points, and when I'm satisfied, I'm going to say that I'm done, and I'm going to say this is not exactly the slope, but it's close enough. Okay. Well, if we implement that in the computer, that does break down. So if we implement the algorithm exactly as I described it in the computer, what's the problem there?
It'll run forever.
Well, you can tell it I want you to run for 1,000 years and then give me the answer, whatever it may be.
Floating point precision.
Floating point precision. Oh, right. This is a problem. Right. If we're doing this on paper, we can, in principle, calculate these points however close we want. But if we're doing this on a computer, then we can't.
It cuts off some.
Yeah. Right. It cuts off at a certain point. So there are two problems. One problem is it could take a long time to run, or the complexity is very complicated. So the nice thing about this, if you think of this as a computation that you want to do, is very simple. But then if you think about that algorithm I described for such a simple expression right here, the algorithm I described is very expensive, estimating over and over again. So it's very expensive. The other thing is, once you get an answer, can you trust your answer?
When the floats get close, it should get pretty wiggly.
Yeah, when the floats get close, it should get, I don't know that I know what that means either. But I'll take your word for it that we can't really trust the answer if we implement the thing that I described. And so the real thing is, if we want to implement it for this function, it's probably great, it's probably fine, because this function is very smooth, which is kind of a way to kind of numerically measure how quickly a function changes. This function is a perfectly fine function, but a lot of the functions that people deal with are not smooth. They're still differentiable, but they're not smooth, and they are, and round-off error is a very big problem. So the
or is this an algebraic expression that's infinitely differentiable or smooth?
there's no data.
It's the nice function
Differentiate
written in the upper
some
right-hand corner of the graph.
Yeah.
Okay.
Yeah. So when I do functional programming, what I do is back to the checking for the null pointer. What I do is I assume that the caller is satisfying their contract. Okay? So I'm not going to worry about where this comes from. Does it make sense? I'm just going to say, assume that we have this picture, and I would like to know the slope of the red line. And if we make that assumption, then I can take you on a ride. And if we can't make that assumption, then we're going to have to stay put.
I want to go on a ride.
Okay. All right. So we have this picture, and we have this equation that tells us the points on here, and we want to know the slope of the red line. Okay. So I get what you're asking, and it is totally incidental to this example. So for this example, just say we could get as close as we want. Okay? So we say
we can evaluate that function anywhere on its independent variable.
Anywhere.
Okay.
Yep. You're right. And with real data, you can't do this.
That's right.
Right. But fortunately, this is a made-up example.
That doesn't mean anything.
Yeah. Yes. Okay. So, we could pick a point that's closer, and we can get a line that is closer in slope to the red line. So this might motivate a question. Well, why are we satisfied with just picking closer points? Why don't we pick the same damn point and plug that in and figure out the slope then? Can we do that? Oh. That wouldn't work, right. Okay, so we're going to have to simply pick closer and closer and closer points. Okay. Now, we can implement this. But I think it's pretty straightforward to implement. I'm not gonna, I was thinking about implementing that, but no, let's not do that. We'll move on later. So what we can do, so the process is, we're going to make an estimate by picking a nearby point. And then we understand that our estimate is not perfect, so we actually form a sequence of estimates. The process I just described is numerical differentiation. You estimate, you make a better estimate, you make a better estimate, and then somehow you decide that you're happy and you're done and you stop. And it has the drawbacks of being computationally expensive, and you worry about round-off error. Okay. So people have been doing problems like this on paper for a long time. And they've been doing it for a very long time. But they didn't make progress until people started to make abstractions. So the abstraction I want to talk about is, we picked a specific point here, and we plugged it into this formula, and we got a number. Okay? This seems okay. Well, mathematics deals with numbers. Okay? So we take a point. Or we take a number, plug it into the function, it becomes a point, and we work with these numbers. The abstraction that we want to do is we want to say, okay, wait a second. Let's not actually work with numbers. Let's take the slope formula. I don't know why I erased it. But let's actually say, you know what? Let's not pick our numbers ahead of time. So instead of picking our numbers ahead of time, I'm going to say this is, say, x1. And let's actually say, what would this formula give us if we plug like a number? Let's do it a little bit easier. Let's say that this is a number b. And so this number would be b squared. And let's say this is a number that we haven't decided yet. Let's call it a squared. And let's do the slope formula, not on numbers, but on these kind of abstract numbers. So we're going to do the slope formula. B squared minus a squared over b minus a. And once we do that, we can start using algebra on this. Okay. So if we had 2 points, this would be the slope. And if we don't know another point on this red line a priori, then at this point, we're kind of out of luck. So that's unfortunate. But remember how we kind of said, okay, well, this line is kind of special. This line is tangent, whatever that means, to this curve. And so what that means is, well, if we zoom in really close, see these points on this curve are very close to the red line. At least if we're close to this point, right? Okay. So what we're going to do is we're going to give up trying to find the slope of the red line. It's impossible. Can't do it because we need 2 points on the line. So what we're going to do instead is we have this equation. This equation lets us get new points, but not on the line, on the curve. Okay, so we'll pick a point really close to 3. Like a number really close to 3 is like maybe 2. Okay, I could probably think of some closer points, but let's say that. And we're going to make this green line. And this green line, we think, okay, that green line is kind of close to the red line. And the green line, it's easy to calculate the slope of. The slope of the green line is 9 minus 4 over 3 minus 2. So 5. So that's really easy to calculate the slope of the green line. But it's not really that, it's not really close to the slope of the red line, as close as we'd like. So there's an obvious thing we can do to get a line that is closer in slope to the red line. What is the obvious thing? Right, scoot this point closer. Exactly.
Question.
Yes.
Where is this data coming from?
Huh?
Where is how is this function defined? Is it defined tabularly? Is it a sampling of some continuous thing? Is it a noisy signal from the real world? Is it a closed form expression?
You said, where is this data coming from?
The thing we're trying to differentiate.
And I am wondering what you mean by this data.
It's a closed one.
Motivating expression.
It's a closed form expression defining some smooth function.
I don't know if I know all the words in that sentence to be able to parse it together. I apologize. But I mean, the thing...
Is this weather data, temperature or humidity?
We're going to talk about automatic differentiation. And before we talk about automatic differentiation, maybe we should talk about manual differentiation a little bit. So I don't want to go very deep into this, but I do want to provide one motivating example. So if you'll bear with me. Okay. The main problem we want to solve is, if you can imagine the following situation. I have this graph right here. And I happen to know that this graph has an equation, the y-coordinate on the graph is equal to x squared. I bring this up because this is like the easiest non-trivial example. So this goes through a couple of points, and one of the points, it's not to scale maybe, but let's say one of the points it goes through is 3, 9. So the x-coordinate is 3, the y-coordinate, use the formula, would be 9. Right. So the basic problem is we're going to draw a red line right here. And that red line, we want it to be tangent to this curve. And what I mean by tangent, I'm not going to say. Just, we can kind of look at that and we can say, okay, that's tangent to the curve, okay. And we want to find the slope of this red line. Normally, when you want to find the slope of a line, you have this handy formula you can use. The formula that you like to use is you take the change in the y values, and you take the change in the x values, and you divide those. And this gives you a measure of how steep this line is. Okay, so this is great. We can use this formula. Now, what do we need to use this formula? Well, we need a point. Here's a point. We need another point.